Hello, today I am taking a look at a paper from Pratodiano et al. Entitled Improving the Security of IPv6 Mobile Signaling Using CAT-SHA 3. This was published in 2021 in the Journal of Engineering, Science and Technology. This team is based in Indonesia. A link to this paper is in the description. It is a short read at around 11 pages. Before starting, I will point out that SHA is an acronym for Secure Hashing Algorithm, is followed by the iteration as a number. This will be divided into multiple sections: the introduction, the experiment with the methods, their results, and finally my conclusion of their work. I will be having some concepts that are applicable to multiple topics in a different type of video called Basics. The introduction. There is a trade off between performance and security and protection when it comes to programming in general. The more secure, the more overhead, the slower the program operates. If you're familiar with my master's thesis, I mentioned having wrappers to direct the provider network to which network slice would be getting the information. The wrapper does add overhead, and this is an added layer of security, though hopefully still keeping it below the latency added by a VPN. There are aspects of IPv6 that speed things up with the overhead when compared to IPv4. I'll explain that on the whiteboard. So here we have IPv4, the version, the IHL type of service, total length, identification flags, fragment offset, the TTL, the protocol, the header checksum, the source IP in 4 ocklets, and the port. Each of these can go up to 255 starting at 0. Options and padding. Now, when considering it going into IPv6, we need to take a few considerations. Converting this into IPv6, we still had the version in the same location, but we removed the IHL. IHL is Internet Header Length, by the way. This. And the total length gets moved into where the identification is. And it gets renamed payload length. In place of the total length, we get flow label, which is basically like the traffic type, and what to do with it. And in this block here, that gets replaced with a traffic. Whoop. A traffic class, which is most of what these flags were used to accomplish. So those are defeated, as is the fragment offset, which was just used to keep this line in 32 bits. These are replaced by the tag for the next header, which is important in the mobile standard, and the TTL, which is named hop limit, which makes more sense. The TTL down here is gone, as is the protocol, since that's also established in the traffic class and the flow label. And we no longer need the header checksum. We end up with more space for the source IP, which is no longer in the IPv4 format. It gets changed to hex values like hex, 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 to a series of 8 of them, with a total length of about 340 trillion addresses possible. But it is also, at the end, you get the port listed. Same goes with the destination address. And I'm not going to redo the H's. Also, to get the added space for that many numbers, we get rid of these options, since they can be handled by putting in the header information in next header. We then, since this is mobile, looking at the next header, which is here, next header, and in here we get the payload protocol, the length of this header, the MHC type, and a reserved space. In the case of updating the SHA version, that information would end up in reserved. And then we get the checksum for the remainder of the box, which is payload. There are other headers outlined by the the IEF, and for IPv6, and I'd encourage you to look at that listed in the description. Thank you. As you saw on the whiteboard, IPv6 has header space for IP security. Sadly, there is a degree of difficulty and insecurity whether the implementation is to be used in IPv6. IPv6 allows for keyed hashing using SHA-1, which was defeated in a security aspect, and you should expect a basics on that one. I would have reworded the statement for SHA-1 to SHA-1 or the latest standard, and have a method of saying which standard of encryption would be used instead of SHA-1. IPv4 had a field in field selection in headers, as does IPv6, so a bit could be used to upgrade the hashing schema. There are benefits for going to SHA-3 over SHA-1. simply because SHA-3 can eliminate black holes, flooding, and wormhole attacks, as well as hash collisions. There will be a basics on these attacks at some point. So now, I'm going to get into how they tested the experiment. I must say they did do a great job with the hardware write-up, so I would recommend taking a look at it. Link in the description. They used a Raspberry Pi 3B Plus as their mobile node, which would be considered a phone. They tested the distance between nodes where their signal would not be overlapping. In this case, it's between a home agent, which would be the home tower, like the one you connect to, at home, and a foreign router, which is a node that you would be connecting to away from home. This is not as prevalent now in the 5G era, but it was a thing in 2 and 3G connectivity. They found with their setup that it was about 30 meters between the nodes where they did not encounter overlap. This experiment was conducted over the network layer, since is the only layer applicable with hashing handoffs and the header when it comes to mobility. I will do a basics on the network stack or the ISO layer, both the same, some point in the future. They set up their nodes with a Linux package known as UCG patched Internet Protocol, which I have in the description as well, set up for IPv6 mobile. This allows testers to emulate network connections between the user equipment and the network nodes, and it can also be used to determine other aspects of networking, which were not covered in this paper. They spaced out the home site and the foreign router 30 meters apart, since that was a distance the Pi 3B Plus disconnected from one and had to set up a session with the other. They then tested the time between connections, the hashing method, authentication code, security at that point, and it was recorded. Look at the tables that I have up here to see their results with the hashing. So, looking at the results they had, they ended up comparing SHA-1 hashing with SHA-3 hashing in regard to connection time and the performance to see if the downsides of using SHA-3 were eclipsed by the upsides of using SHA-3. For testing, they were sending data for a file name and hashing with the SHA algorithm to see the results. I do recommend looking at the results in the paper. SHA-3 will change the hash based on file name, and SHA-1 does not. Hash length does not impact the output hash using SHA-1, but it does in SHA-3. It appears that SHA-3 adds 500 nanoseconds of overhead at worst compared to SHA-1. My conclusion is it appears that the delay added from SHA-3 is worth it for better security, since the difference is less than some network lag you would encounter without using SHA-3. Quite simple, but furthermore, technology will advance, making decoding on both the network and the user node end, therefore mitigating the issue. This is a simple paper, but it gives insights to issues with writing standards that are not forward thinking and the delay that can be introduced when implementing stronger, actually non-defeated standards. It's a good paper. Recommend giving it a read.